Okay, I think everyone already knew that. Just a quick reminder that homework 5 will be due this Friday. So so basically on this Friday, I will also be posted the homework 6. So homework 6, the next one will be the very last homework for this semester, because this week is actually week 12. So we only roughly have 3 weeks left. And so the very last homework 6, will be due on the essentially the last week of the class, and then it will be and then the following week will be the final exam. Okay, so today our goal is to pretty much first, there's still a few things that I want to mention about pullback of the covector field. So I'm going to first recall what's the definition by pulling back a covector field by a map. Okay, then once we can define that, then we're going to take a look at some property for pullback of a covector field. And so, for example, we can actually use that to do a lot of computation, and also some of the property. And then the next thing we want to do, which essentially is the main thing why we want to define the pullback for the covector field, is to use it to define how to do the line integral on the manifold. So essentially, like you can integrate a covector field along a smooth curve on the manifold. And the way we define it is by pulling back the covector field from the manifold to R, right? Because if you have a curve, the curve would look like a map from some interval on R to the manifold. Then we essentially, the definition we are going to use is that, okay, then how do we define the integral on the manifold? We do it by pulling back the covector field to the domain, right? From the image to the domain. Then it will be a smooth covector on R. And then so first what we're going to do is to make sense of the integration of a covector field on R. Then we can define an integration of covector along the curve on the manifold. And that's the goal. Okay, so once we see that, like how to do the integral of a covector field, or in other words, one form on the manifold, then we can generalize this idea to do the general integration, right? So essentially, if you eventually, hopefully, we can reach that far that we can essentially integrate an n form on the manifold. Okay, that's the very final goal. Okay, so first let's recall what does that mean to pull back a covector, right? Covector field and covector, the only difference is that if you evaluate a covector at a point, then essentially you assign me a covector. So first we need to know how to pull back a covector. Then we can pull back a covector field. So we saw this last time. I just since it's been like over the weekend, so I want to also recall this definition. So that's let's say if you have a smooth map from a manifold M to N, then this is what we call the dual map of the differential, right? So the usual differential map is from the tangent space of M to tangent space of N, right? Now you want to do the dual of this map, then essentially you need to flip everything, right? So the dual, we usually use a star for the dual. It's similar as what you saw in real analysis or functional analysis when you define all the dual map. Then it's from the dual of the codomain to the dual of the domain, right? So this basically you input a covector on N and output a covector on M, right? So this is what we call the pullback, because essentially everything is from M back to M. That's why we say it's pullback. So compare this with the push forward of the vector field later, that we defined earlier, right? So the reason we call it push forward is because you send it through the differential, right? So you send it from the domain to codomain. Now it's backward. That's why we say it's pullback. And the definition is very straightforward, and it's actually quite natural. So basically you have a covector. So a covector is really nothing else but a mapping from the tangent space to R, right? Tangent space of M, right? So you input a vector, output a real number, or you can think of it as a linear functional on the vector space. Sorry, this is N. I'm now on N because it's the covector on N. Okay, so you have a covector on on N, right? then as I said, you will, if you input a covector on N, then the output should be a covector on M. So you can see that after you do the pullback, this should be a covector on M, right? Then in order to understand explicitly what this covector is, then because it's a covector, so you want to plug in a vector, right? So if you plug in a vector, because it's a covector on M, so you should plug in a vector on the tangent space of M. And you want to see that how you defined it. This is the definition, right? So the definition is, okay, all we know about this thing, the information is the covector W, right, or omega. And also we only know the differential df, right? So basically what we're going to do is to use this to define our pullback. So the pullback is, in some sense, you can argue that the pullback also depends on push forward, in the sense that you can see that the definition here is that if you pull back W, it's a covector. When you evaluate or input a vector V, then the definition is you take W, right? And then you input this vector, right? So this differential of V is a vector on, the tangent space, right? So then, and W, as we define, W is a covector on N. So it makes sense to plug in a vector on the tangent space of N. And that's how we defined it. So you can see that essentially, in some sense, the definition of pullback depends on the push forward of your vector field, vector V. So that's essentially how we define. And then it's actually quite natural in the sense that that's the only way you can make sense of this. I mean, the only information you have is a vector V and W. How are you going to make it work? I mean, this is the only natural way to define it. So now once we know how to define a pullback of a covector, then we can define a pullback of a covector field. Okay, so the only thing we need to do is that if you give me a point, I want to see that how to pull back every covector at different point, right? That's essentially the covector field. So last time we also defined this, that let's say you have, again, you have a smooth map from M to N. And now this time I'm going to abuse the notation a little bit by calling the same W, but now it's a covector field. Okay, so when you evaluate at a point, it will be a covector. So now I have a covector field on the codomain N, right? And when you do the pullback by the smooth map, so last time we mentioned that the way we define pullback is always well defined. Meaning, if you later on you check, if you pull back a covector field, it will always be a covector field. There's no ambiguity that which point we're talking about. Because the things that when we say pull back by F at P, we actually already know that what's the corresponding like image, it's F of P. So later on, you're going to see there's no ambiguity. So it's actually, in some sense, has a better property than the push forward, because push forward, you need to be careful, right? If your map is not injective or surjective, then there will be a problem that, for example, whether you have the corresponding image, right? Or maybe like you will send two different things to the same image point, and they will cause some ambiguity. But pull back is fine, because pull back, when you say pull back at P, you actually kind of pull back from F of P. But once you give me the point P, F of P is uniquely defined, right? If you give me a fixed point P, F of P is definitely well defined. So pullback has a better property than push forward. So the definition we defined last time is that, okay, if you have W, which is a covector field, then first we can define another covector field by this is what we call the pullback of this W by F, right? And the thing is that right now, we only know that when you pull back this W, it will be another covector field. But we don't know whether it's smooth or continuous or not. So that's why we say initially, we know it's a rough covector field, meaning it may not necessarily be continuous. And the definition is the following. When you evaluate at the point P, right? So first, this F star W is the pullback of W, right? And it should be a covector field. So how to define this covector field? I say when you evaluate at P, it will be the same as using the above definition, right? So basically, we know how to pull back a single covector, right? So how do you pull back the covector? You essentially pull back the covector from the point f of P. So you essentially pull back the covector, which is essentially W evaluated at f of P. And you pull back using the dual map, DFP star here. And that's why there's no ambiguity, because once you tell me I want to pull back to P, the only point you can pull back is from f of P, right? So there's no ambiguity which f of P you're talking about. Once you fix the point P, there's only one f of P, right? So that's the main difference between pullback and push forward. So that's why in some sense, this is better, okay? And to be more precise, if you want to see explicitly definition that like when you, because each of them, this is a covector, right? So you want to see when you plug in the vector, well, how does it act, right? What's the definition? So essentially, when you evaluate, or essentially you should say, when you input a vector here, then the definition by using the definition above, right? So we know that following from the pullback of a covector here, then this will be our definition. So when you pull back the covector field W by F, when you evaluate P, it should be a covector. So in order to see what this covector really means, you plug in a vector here, right? So for any vector V on TPM, I want to see how to define it. Then the definition is essentially from the above, right? You essentially take W but evaluate at f of P. And the vector you should input now is the differential df of V. Okay, so that's essentially like we combine the above definition altogether. So that's, you can probably most of the time people use this one because this is more explicit, because it directly tell you how to evaluate at how to input a vector V here. So either way, sometimes we will switch between abstract definition with the one that carry the vector V. Okay, but you should know both. That's what I'm saying. Okay, so essentially from this definition, you can see that since there's no ambiguity of which point you should pull back from, right? So that's why a covector field will always pull back to a covector field. It's definitely a well-defined definition. So we don't really need to require, for example, like the map F to be diffeomorphism. There's no need. The only thing you need to require is being a smooth map, right? That's why it's less restrictive compared with the push forward. Okay. So now last time I remember this is the thing we stopped last time, that we have this nice tool in some sense that were going to be very helpful for our future computation. So this says that, okay, if you have this smooth map F and you have this continuous real value function, meaning on n, right? Meaning from n to r. And you also have W to be a covector field on n, right? From now on, you can see that most of the time our covector field would be on the codomain because we want to do the pullback, right? And there's two things we can prove. First thing is that if you take this continuous function U times W, this would be another covector field, right? It's similar to what we saw in vector field. Back then, if you have a vector field X, capital X, you can multiply X by some function F, right? F times X will give you another vector field. Same thing here. If you multiply a covector field by another function U like this, real value function, then you will be another covector and covector field. Then you can do the pullback of this covector field, new covector field. And the way you calculate it, it will turns out to be, in some sense, the pullback of both of them. So you will have the pullback of U, right? You can think of that. This is the same pullback we saw in one of the homework. I forgot. I think it's homework 3, right? Homework 3, we have this pullback of some function of the, like you pull back a u by another smooth function, right? And this is essentially composed with f. This is what we saw in the homework. So in some sense, you have a pullback of this function, right, times the pullback of the covector field. So it's actually not hard to memorize at all. And another computation involves a pullback of some differential. So if this u, that the real value function u is actually smooth, then we can actually define the du, which is the differential of this function. And it's actually a covector field, right? This is the differential. And differential du like this is a covector field. This is exactly the homework you're doing right now. So if it's a covector field, we can definitely define the pullback, right? We can calculate pullback. Then the pullback of a differential like this, du, will be the differential of pullback of u in some sense, right? So it will be d, differential of u composed capital F. So all these two statements or two equations, we can actually directly compute it or derive it by the definition. And like actually this proof will be, if you see the proof, you will see that it will actually practice the understanding by using the definition. So let's prove the first one first. So if you want to say that, okay, whether the equality holds on both sides, right? So what you want to do is that if you want to, there are two ways to prove that two covector fields are equal. First way, you want to say that when you evaluate at point P, the left-hand side will equal to right-hand side, right? The covector you get when you evaluate at P should be the same as the covector you get when you evaluate on at P on right-hand side. That's one thing. The other thing is by going through using the tangent vector, right? When you plug in the tangent vector, you hope the left-hand side will give you the same thing as the right-hand side, right? So either you can just do the abstract definition check, or you can go through the tangent vector. Depends on which one is easier or more straightforward, okay? So first one, we are going to see that, okay, for this pullback of the covector, okay, I want to evaluate it at P and see what does it looks like, right? So now when I evaluate at P, it becomes a single covector. And by the definition of pullback of covector, right? Then this is really just say, okay, I'm taking the differential, the dual map of the differential, right? And then I essentially want to pull back this single covector. But when I pull back, I'm actually pull back from the value at f of p, right? This is actually using the star definition above here, right? So let me maybe say the star here. Okay, so now let's see. So then what would be this, right? So let me write one more steps. So when I evaluate at f of p, right, this is nothing else but you put the covector field looks like u at f of p, right? And you also have the covector field evaluate at f of p. I just kind of expand the notation here. So now I want to pull back this covector, right? But now if you notice here, this dual map here, so you have a dual map of a linear map. You can check by our definition, it's actually linear. So this map is linear. So if it's linear, I can factor out any scalar, right? So this is a scalar here, right? Because u is a real valued function, right? So when you evaluate at point, it's a scalar. So you can actually factor out the scalar here, right? So the remaining part is only the pullback of this particular covector. And if you see, then this is really the definition of pullback of this covector field at P, right? So let me just rewrite this. So I can also rewrite the u of f of P like this. This would be u of f, right? And times the pullback of the covector field. and everything evaluate at P. So I'm just keep playing around with the definition. Some of them, the notation might be a little bit like redundant, but this is just really by everything is by definition. The only extra thing I would say is by the one thing you need to be careful is just when I factor out U, I'm using the property of the dual map to be or you can say the pullback to be linear. So you can see that now that's why you can essentially evaluate this as the pullback of U times pullback of the covector field W. That's the first state equation. And second one for the differential, right, for du, this time to be because if you remember how we define differential, right, df or du, whatever, we actually need to define it by acting on the tangent vector, right? We define, say, df of v is v acting on f. That's how we define the differential back then. That's why in this case, it will be easier or more straightforward to use to go through the tangent vector. Okay, so now let's see. So when we go through the tangent vector, so I want to see that, okay, on one side, I have the the pullback of the du differential, right? I want to evaluate at P, right? And I want to see when I plug in the tangent vector, hopefully, eventually it will give me the right-hand side, okay? So now let's see. So by the definition again, right? By the definition of pullback, that's the start, right? So what we have is that, okay, then essentially this is kind of play with the notation. So this would be essentially you take the dual map, right? And you pull back this differential. This is a covector field. But this time when you pull back, you always pull back from the corresponding image, right? So you pull back du as a covector field, but the covector you pull back is at the point f of p, okay? And once you do this, this will be a covector at p, and I want to plug in v, okay? Now let's see, then you can see that from the above, right? This is this is what we actually have here, right? If you plug in the vector v, right, then this is as if you're taking the differential, right, df of v, and then you're plugging into the original covector w. So essentially, again, by the definition here, what we're going to do is, okay, if I want to pull back this covector, what I want to do is, okay, essentially, I want to take the value of this covector field at fp. But what I input now is the differential of v through this map df. Okay. So now at this point, it backs to the definition of differential du. So first, if you treat this as some, I don't know, vector, let me call it, I don't know, like call it like, yeah, some w vector, right? So du of some vector w, it will be w acting on u, right? So this is this is by definition of differential of u. So this would be whatever this vector is acting on u. But now we keep going through the definition, right? You have differential of a vector acting on u, right? This is essentially the same as this is the definition of back to like chapter 3 when we talk, or chapter 2 when we talk about differential, right? So this is essentially taking v acting on u compose f. And eventually, after you got here, then this becomes going back to the differential of U compose F. So this is by definition of differential of U compose F. So I'm just kind of go back and forth between all the definition here. So if you haven't catch up this far, this would be a little bit like confusing to you, because you need to play around back and forth between all the definition of differential of some function and also differential of some vector. So you need to actually be very, very familiar with the definition here. But this is actually, I'm kind of doing the same thing as the textbook. So you can, the textbook actually do a very thorough, like step-by-step like this. So you can actually compare later on when you review the context, you can actually compare with the book as well. Okay, so any question so far? Okay, so now we want to put this into use. So this is, this is 11.25. So before we really take a look at an example, actually, once you see the example, you will see that this is just, this formula will help you to do the computation, but the computation in some sense are even more intuitive than the formula here. So another thing, before we see an example, another thing I want to just quickly justify is that back then when we pull back a covector, we say that, oh, we actually, initially, we only know that it's a rough covector field, right? So F star W, it's a rough covector field, meaning we don't know whether it's actually a smooth covector field or not, right? And as you can imagine, the smoothness should depend on whether the covector field you pull back is smooth or not, whether W is smooth or not. So the following proposition confirms that. So if you have a covector field, when we say covector field, usually when we say that if we don't say anything, we actually means it's a continuous covector field at least. So when you pull back a continuous, at least just a continuous covector field, it will be a continuous covector field, right? So F star W is continuous. But if in addition that we know W, this covector field is smooth, then you will pull back to a smooth covector field, right? It actually kind of makes sense, right? So then we can actually directly see it by using the component function. Remember, one of the way we check whether a covector field is smooth or not is by represent it in terms of local coordinate. And in each local coordinate in coordinate chart, you will be able to write W as, for example, some component function Wj times dyj or dxj, depends on the coordinate you use, right? So then by knowing whether the component function is smooth or not, that's how we check whether the covector field is smooth or not. So we do the same thing. We can write F star W. We can write this pullback of the covector field in terms of the coordinate. Then we can see what would be the corresponding component function looks like in terms of local coordinate. So, but then in order to do that, we need to set up what's the setting here. So for any point P at in M, right, we want to, because once we fix a point P in the domain, we already know, then we are going to pull back the covector from f of P, right? Then essentially you pick some smooth chart. And this time, because it's in codomain, so I'm going to code the coordinate to be yj. And the smooth chart is essentially, the one I pick is in the neighborhood of the corresponding point f of P. And then we use f inverse of V to be my open neighborhood, the chart that I'm talking about for the neighborhood of P. Then in this case, in this neighborhood, I can write W in the local coordinate. So as I said, it will be some component function Wj times the basis of my covector field, right? So this is very similar to what you saw in vector field. But now because we're dealing with covectors, so the basis become dyj, right? So compare with the partial xj, for example, that's the basis for vector field. This is the basis for the covector field. then so you have this continuous function, the component function wj, right? Now, what we're going to do is we essentially want to pull back this w, right? This covector field. Then when you pull back, you will see that this whole thing looks like a real value function wj times the coordinate covector field. And we want to do a pullback, and this becomes what we saw here in 11.25, right? You the first one, you have some real value function times some covector field. That's why we can use 11.25 twice in some sense. So now let's see. So now I want to pull back, right? So, okay, I first pull back w, right? Then in terms of local coordinate, in each coordinate chart, I'm going to pull back things like this. So here I omit the summation notation. Keep in mind, everything here has I'm using the Einstein summation, right? So I essentially add up the index here. So now this is where we use the 11.25 just now, right? You pull back a covector looks like some real value function times another covector, right? So we already know then it's as if you do the pullback of this component function times the pullback f star of dyj, right? But you can see that dyj is essentially the differential of coordinate function yj, right? So you can see that this part I'm going to use 11.25 again, right? So this is actually, you can see that, okay, I keep the wj composed of f. This is just some scalar function here. Then times, so this is the part 2, right? 11.5 part 2. This is 11.5 part 1. Okay. So now you can see that then this is really the differential of yj compose f, right? But if you think about what's yj compose f, right? So f is a map from m to n, and yj is the coordinate function. That means you are actually taking the differential of j's component function of f. So this is essentially, let me rewrite it. This is, you can call this fj. So this is the j's component function of f, right? So in some sense, you can also rewrite this. I mean, sometimes it might be helpful to think of this as something like the differential of fj, right? Either way, right? So, but the thing is that what we need for this proposition is actually here. This is the new component function we want. This is the component function. Component function, right? So you can see that that's why if we don't know whether w is smooth or not, let's say if w is only continuous, then you can see that this part, the component function here, will be like just continuous, right? And of course, you have this dfj here, so you need to actually do like some other computation, right? You need to take the differential of this fj. Then there will be some like derivative of f coming out times dx, blah, blah, blah. But f is already smooth, so we don't need to worry. So the only thing that we worry is this part here. So it really depends on whether w is smooth or not. As you can see, if w is smooth, then this component function wj will be smooth. Then, I mean, capital F is already smooth, so this whole thing will be smooth. So that's why whether the pullback of a covector field is smooth or not, depending on the thing you pull back. Okay, if the W you pull back is smooth, then we are fine. Okay, so I'm going to be a bit sloppy here. Like I just want to like say it instead of writing the complete sentence. So you can actually compare with the textbook proof. So basically, this just tells you that if you pull back a smooth covector field, then the pullback will be smooth. Okay, so now I want to really do a one example. This is also an example I pick up from the textbook. So you're going to see, as I said, the computation is quite natural. It's more straightforward than in some. I'm using the formula above, but it's more intuitive to just directly compute it. So I have a smooth map from R3 to R2, and it's mapping from XYZ to X squared Y and Y sine of Z. And so I'm going to put the coordinate XYZ for R3, but for R2, the coordinate will be UV, like what I wrote here. Okay, now I want to compute the pullback of this covector field on R2. And this covector field looks like, because it's in R2, right? So you have, the one I pick is U times dV plus V times du, right? So now let's see, what would be the pullback of this W looks like? And as you can imagine, everything, because it's from R2 back to R3, right? So your eventual, like the result should be some covector field in terms of X, Y, and Z, right? I should say in terms of dx, dy, and dz. So now let's see. So using what we have back in, like in some sense here in this step, I'm using proposition 11.25, right? So again, you can see that you have, or maybe 2.6, depends on how you view it. So you have U times dV, right? And then another function, real value function times a covector. So what you're going to have is from the previous two proposition, you're going to have the pullback of your real value function times the pullback f star of dV, but we already know it's going to be dV of f, and plus V evaluated at f times the U of f. So the only question is, what does each part means, right? So you can see that first, let's deal with this U of f and V of f. So it just means that U is the first coordinate of R2, right? But you compose with f means that you're essentially calculating using the component coming from f, right? So this part is really just the first component, right? So you are picking out the first coordinate from the map capital F. And this part, it just means that you are taking out the V of F is the second coordinate of F, right? So you're doing differential of second coordinate of F. And do the same thing. So here you have V of F times differential of U of F. And this differential is really what you were calculating in the homework right now. Now you can calculate the differential, right? So you have differential of some function in terms of x, y, and z. So you need to do the partial derivative, right? So you will have partial f partial x times dx plus the partial derivative with respect to y times dy plus partial derivative with respect to z times dz, right? So you're going to have several terms here. So let me keep the x squared y here. So the first part, you're going to have partial derivative respect to x, that's 0. So I'm just going to write it down anyway, so you can see the whole formula. Right, that's the first part. And plus y sine z times the differential of x squared y. So again, you will have partial derivative with respect to x dx plus same thing. X squared y partial dz. Okay. So now, I mean, this is really just the calculus, right? So this is 0. We don't have this, this is 0. Okay. So I'm just going to give you the final thing so you can actually see it. Actually, let me still write down the middle step in case the confusion. So I have sine z dy plus y cosine z dz plus my sine z dx, that's 2xy dx plus x squared dy. Okay, so if you combine everything together, this is really just algebra here. just really expand everything and then arrange it in terms of dx, dy, and dz. Okay, so I expand actually more detailed than the textbook, so you can actually compare with it. So it's actually not hard at all in the sense that once you reach the first step, you can see the only thing you were doing is just technically, intuitively, you replace. So when you do the pullback, in some sense, you're just plugging the corresponding coordinate coming from the map, right? So for example, you know that the W is U dV and V du. So the only thing you say, okay, U is the first coordinate, V is the second coordinate. After I pull back by F, what does that mean? It means that you replace the first coordinate by whatever given from the map F. And you replace the V, the second coordinate, by whatever coming from map F. And you do the corresponding differential, right? So this is actually quite intuitive in some sense, the pullback, right? So actually the computation is not hard. It's very straightforward. So there's another example you should definitely take a look, which is similar, but you can view the pullback as some kind of change of coordinate. Then this is essentially the formula I was mentioning in the homework hint as well. So you should definitely read this. Like it will give you another point of view doing the pullback. Okay, now, sorry, any questions so far? Okay, so now I want to finally, once we define or we can do some computation on the pullback of a covector field, then we can finally define the line integral here. And as I said, first we need to make sense that if we have a covector field on the real line R, how do we do the computation? Once we can define that, then we can move forward to define the line integral on the curve. Oh, sorry, on the manifold through along a curve. Then essentially what we did is by doing the pullback of the covector. Okay, so now let's see. So first, if we can understand how to do the integral on R, then we can define the integral on M. So let's say if we have a compact interval, right? And we have a smooth covector field on this interval, compact interval. Then because we have, for R, what's nice about R is that we have a global chart, right? We only have one chart. So in this chart, essentially the global chart, you can see that when you evaluate your covector field at each point, you can rewrite it as some scalar function, right? F of t times dt. That's a covector field on R, right? I think one of our homework also we see something like this, right? And this F, because it's a smooth covector field, so I need the component. This is the component function, right? So this is component function. Okay, so you have a component function times the basis, but since it's in R, so we only have one covector as a basis. So this is just dt. So once we can rewrite a smooth covector field on the interval as f of t times dt, and this should be defined globally, then we can define such integral. Okay, so we can define the integral of this covector w over the interval by the following. And you will see that this really looks exactly like the usual like integral on R, right? In Calc 2, for example, right? So when you define, how do we define the integration of this covector field W over AB? The way we define it is really just do the usual integration in R. And the function you integrate is really f of t. Okay, so this is actually why it makes so much sense to do the integration of covector field, right? So now the question is, like, what we don't want is that, so because it kind of relates to the original integral we know on R. So what we want to be careful is that if we somehow do some kind of change of coordinate, right, or repenetration, something like that, we want to make sure that it doesn't change the value of your integral, right? So the first thing, usually when you define such things or such property, especially later on the manifold, we want the property to have some sort of invariance. And this invariance should be invariant under diffeomorphism, right? Because as you can imagine that if we have some diffeomorphism between, say, an interval in R and interval, then in some sense, like in terms of like smooth manifold, right? Those things are the same. So the structure is the same because they're diffeomorphic. So we don't want there's an ambiguity when you integrate over specific penetration or over the other specific penetration. So this is the first thing we can see is that the integral that we define here actually has like diffeomorphism invariance. So in the sense that if you have a increasing diffeomorphism, right? So in some sense, you can think of this as essentially like a change of variable. So W, again, it's a smooth covector field on a compact interval. And if we have a diffeomorphism between another intervals in R, C and D, to A and B, right? And here I need to emphasize this is an increasing diffeomorphism, right? So essentially when you do the representation or change of variable, it's essentially in the same direction, right? Then in that case, when you pull back your same covector field by phi, right? So when you can see that because W is defined here on AB, right? So when you pull back, it will be on CD, right? Because this is the pullback to the domain. So this would be a covector field over CD. Then the integral over CD of this pullback should be the same as integral of W over AB. So this is what we call the diffeomorphism invariance. In some sense, you can think of this as exactly the formula for change of variable for the integral that you know before, the substitution, right? So we can easily quickly check this just by going through the definition. Okay, so now let's see. So what we're going to have is like, first, I want to see that what's this thing looks like, right? This pullback, right? So this pullback here, essentially what looks like, so I want to, actually I need to set up a little bit more. So sorry, before we do this. I want to define the variable I'm using. So I want to say that because now I have T is the variable I use on AB, okay? And for CD, I'm using S as my variable, okay? So that S be the coordinate on CD. And that T be the coordinate on AB. Okay, so in other words, I'm thinking T equals phi of S, right? That's the variable I'm using, okay. Okay, so now with this, then I can check what would be the phi star W evaluate at S, okay. So now, this is really just first by definition, I'm pulling back W, right? So W is, we know that it's f of t dt, right? But now when you pull back, again, this format, we are using the 11.25 again. So this is essentially f composed with phi, right? And here you have the t of phi, but essentially, because there's only one variable, so you will actually get the phi here. Okay. So now with d phi, then by definition of d phi, this is differential of phi, right? And this everything is only one variable. So you have keep the f of phi, then this is the definition of d phi. right? If you only have one variable, then differential of that thing is really just taking the derivative with respect to the corresponding variable. So here, essentially, I know explicitly what phi star W will looks like at each point. Okay. So now up to here, now I want to integrate on both sides. Okay. So on both sides, I have the integral of pullback of W over CD. And essentially, I know that in terms of the component, right, phi star W in terms of component function, you have this whole component function times ds, right? So then by definition of the integral of covector, then this is really you, because now everything is on real line, you can really just integrate this thing. This is the usual like single variable integration on R. But then now we can do a change of variable because we know in calculus how to do the change of variable. So this is change of variable. Or actually, I want to recall in calculus, we do have some such things. So let me use G and F. Probably this is easier to see. This is like a U substitution. We have a thing like this in calculus, right? If you call U equals G of X, that's what you're going to see. So this is the change of variable in calculus. So then after this, what you're going to see is that this is really nothing else but f of t dt. If you think of t is phi of s, right? Then this go back to the definition of integral of omega and w over ab. So that's why from one side, when you integrate, you have phi star w, but it will actually be w here. And here, the reason why it keep the sign is because it's an increasing diffeomorphism. So when you do the change of variable, it will not switch the endpoints of integration, right? You can imagine that if you have a decreasing function, then you will switch essentially you will have a smaller value as a endpoint, and then initial value will be larger. So you need to actually change the integral. They will create like a negative sign. So be careful that this formula works if your diffeomorphism is increasing. In some sense, it keep the orientation, right? You keep the direction. But as you can imagine, that if this is going to be the same sign when you have a decreasing function, decreasing diffeomorphism, then it's going to be negative. So this is the remark here. You can actually prove it yourself. The only thing it's going to have change the sign is in this step when you do the change of variable. That's when you have a sign difference. So when you have a decreasing diffeomorphism, then when you do this pullback by this diffeomorphism, it's going to be negative of the original W over AB. So this is really just by first the definition of what would be the integral of W looks like over some interval. And then since the way we define it is really through the original, like usual calculus, like the usual integral over some interval in R. That's why all the property we saw in the usual single variable integral is going to carry here. And it's just like the way we define the pullback of W, it's actually nice. So it actually fits the integration here. Okay, so this is actually first important thing, because this is going to, we definitely need this later on to define to make sense or make the definition of manifold well defined. So now we know how to compute or define the integral of some covector field, smooth covector field on R, right, or on a compact interval in R. Then we're going to see how to generalize this concept to manifold. Okay, but to manifold, if we want to do such line integral along the interval, then the more intuitive situation would be you define the integral over a curve, right? Because I mean, it does not make sense to talk about interval on a manifold. It makes sense to talk about curve on the manifold. So now before we can generalize to the curve, there's several terminology I want to introduce. First, we can, the textbook use this this terminology. They call like a curve to be a smooth curve segment. And this is really just means that they are going from a compact, again, you're going, your domain would be compact interval to a manifold, smooth manifold. And if it says smooth, right, curve segment means that you treat this map gamma to be a smooth map between manifold, and the AB here, you should treat it as manifold with boundary, right? Because it's now a closed, like a compact interval. But when we back in chapter 2, I think, when we define the smooth map between a manifold with boundary, the way, how do we deal with the endpoint? What we really meant is that this gamma will has, give me a second, my notes drops. Okay. So this really means that the gamma will have a smooth extension to the neighborhood of the endpoint, right? Remember when we defined the everything smooth, like for example, if you are in the upper half plane HN, right? How do we deal with the smoothness on the boundary? Then we say, okay, we actually can extend the map. We have an extension, smooth extension, right? So basically it means this gamma will have extension to a smooth curve defined in the neighborhood of each endpoint. That's it. Okay, so it's a smooth curve from a compact interval to the manifold. But if we definitely want to make it a little bit general in the sense that in most of the situation, we may not be able to find a smooth curve, complete smooth curve. But what we can do is with a piecewise smooth curve, right? So we define the piecewise, I mean, I think we saw this in calculus, definitely. We can define piecewise smooth curve segment. What we say that it's a piecewise smooth curve, meaning you can find a finite partition, right, of the interval, right? And when you restrict to each subinterval, it's smooth, right? So the typical picture you're going to have is something like this, right? So you have, you might have a singularity, right, non-smooth part, but each part is going to be smooth, right? So each interval is going to be smooth, but you might have some sharp corner, something like that at finite point, right? And we can actually make sense of integration over such interval, right? It's like imagine when you do the usual integration, if you have one discontinuity, you can still define the integral, right? At those piecewise smooth curve. Okay, so now we can define the integral of a covector field on the manifold on either smooth curve or piecewise smooth. Okay, so the definition is the following, and it's quite intuitive. So let's say now you have a smooth curve on M, right? Smooth curve segment, and W is any smooth covector field on M. Then we can define what we call the line integral of this covector field along the curve, right? To be the following. So this curve is on M, right? So you're doing an integral of W on M, but the definition is actually through the integration on R, right? We already defined how to compute the integration of a covector field on R, right? So we only know what's the definition here. So the definition of line integral on manifold, essentially you pull everything back to R and do the integration, right? So basically the definition is the following, that the integral of this W on manifold is the same as you pull back the W by the curve gamma, right? So the gamma is actually from, so you have AB to M, right? This is gamma. So you have an omega here, right? Then you pull back to a covector here on AB, then everything is on R. right? So now essentially you have a covector on R, right? So this is an integral on R, right? So essentially that you have this this gamma star W is a smooth covector field on AB, right? And we already know how to define it. Once you can explicitly find the, the component function, then you can actually integrate it over R. So that's why, in some sense, that once we know how to define the integral of some covector field on R, then we can kind of generalize it to the situation on manifold. And the way we do it is really through the pullback. That's why we really need all this pullback thing. Is essentially the goal is to be able to define the integral, such integral through the pullback. And what happened if the curve gamma is piecewise smooth instead of everywhere smooth, right? Then you can imagine, because then it's just a piecewise smooth, right? So you can define it by doing the integration on each piece, right? So it's actually not bad at all. So we can define, if gamma is just piecewise smooth, then we can define the integration just to be the summation of because it only makes sense to integrate the smooth covector field there, right? So we essentially pull back the covector W, and you doing the integration on each smooth piece, right? And you sum them up. It's like when you do the integration in Calc 2, right? If you have some discontinuity point, right? Then you can add, if it's finite discontinuity, then you can still do the integration. It's not going to affect the value of the integral. Okay, so before we do some computation, there's several nice property about the integration. As you can see, that the definition of integral of W really relies on how do you do the pullback, right? And also, once you do the pullback, it becomes just the usual integral we know on the real line, right? So anything we know about the usual integral, right, on real line, it should have here, right? For example, there's a linear property and all that. So first we can see that there's several nice intuitive and natural property that we can have. And here the curve that we compute the line integral for, it's actually only need to be piecewise smooth, right? All the integral here, like in general, we're going to be able to do all the computation on just a piecewise smooth curve. So now you can see the first one is, okay, if you integrate the linear combination like this for two covector W1 and W2, then you can do this is essentially the linear property, right, for the integral. And this is true for any real number C1 and C2. And sorry, this is W1 and W2 here. And also the second part B says that if you have gamma to be a constant map, what does that mean to have a constant smooth curve? It means that if you map from AB to something in M, right? This is M. Then instead of really having a curve that's moving, it means that you just map to single point, right? For gamma. Then that means you're doing the integration over a single point, then this is going to be just 0. You can check it by definition. When you do the pullback, you are going to take the differential of a constant map that will give you 0 eventually. And we also have what we call the additivity property, right? So this is what we saw in the usual integral, line integral before, like one variable, right? If you have, if you cut the A to B into two sub-interval, non-overlapping, right? Then you can actually add up the integral. So the integral of W over the whole curve will be the same as the integral over the part from A to C, and also the part from C to B, right? That's, I mean, we already kind of expect this should happen, okay? Then the last one is the really nice part, that this is somehow, in some sense, the change of variable, or just essentially the nice like repenetration in some sense. So if you have a smooth map, right, and you have like the covector field from N, right? So when you pull back the covector field eta by F, right, then this will be a integral on M, right? Because the gamma is a curve on M. Then this integral should be the same as the integral of eta, but over the curve F composed gamma. So this is an integral on N, right? So, but then you can see that F composed gamma is another smooth curve or piecewise smooth curve, right? So you will have this nice property. So I'm actually thinking about maybe making this part D as a homework problem. Okay, but all of the proposition 11.34, you should be able to do it through the definition of the integral using the pullback. Okay, so now let's see one example here, so we can really do the computation. So again, the computation is quite intuitive. So you have this manifold, if you want to call it manifold, it's really just the R2 without the origin. And you have this, first we can take a look at the covector field on R2, right? So you have this W, this is a covector field on R2 without origin. And the definition is x dy, x essentially had put in the denominator here. So it's x over x squared plus y squared dy minus y over x squared plus y squared dx. And I want to compute what would be the integral of W over the following curve. So this curve is a curve on M, right? And as you can see, the definition of gamma is really cosine and sine. This is nothing else but just a circle, right? So you have a R2 without, right? And this is a circle. Actually, you can even tell me what's the orientation, right? Because T is from 0 to 2 pi. So it's starting from here and back to here, right? So this is a curve counterclockwise circle. Okay, now I want to see how to do the integration of this covector field over gamma, right? So then let's do that by definition, right? This is gamma is really just the, so by definition of integral, line integral, of omega, right? So we do it through the pullback, right? If you want to integrate W over gamma, then this is the same as integrate the pullback of omega by gamma. And the domain will be, in this case, will be 0 to 2 pi, right? You pull back everything back to R. Okay, now the question is, we really need to compute explicitly what would be gamma star W looks like, right? But we already did it before in the sense that when you do the pullback, it just means that you replace the coordinate by the corresponding coordinate coming from the map, right? So here, as you can see that gamma give me the first coordinate to be cosine T, and this is sine T, right? So like the previous example we did, when we see X, we just replace X by cosine. When we see Y, we replace Y by sine, and you do the computation there, right? So basically now you're doing the integral of over 0 to pi, right? And okay, so cosine, you replace X by cosine. And actually X squared plus Y squared would be nice because it's cosine squared plus sine squared is just 1. And dy will be d sine T, right? Minus Y is sine T and dx. So this would be a covector field over R, right? But now before I can compute the usual integral in R, I need to really expand to see what d sine T looks like, right? So I need to do a little bit expansion. So this would be, I need to do expansion for d sine T and d cosine T. So this will have cosine T here, and d sine T will be, I mean, this is just one variable. So take the derivative of sine respect to T and times dt, right? And I have another minus sine T times derivative of cosine, that's minus sine, dt. So you can see now this is the usual integral over R from 0 to 2 pi. And you have cosine squared dt plus sine squared dt. So this is really becomes super easy. This is just 2 pi. Okay. So you can see that by really explicitly knowing what the curve looks like and what my covector looks like, I can explicitly compute the integral of this covector field by using the pullback, and I pull back everything to R. Then I know how to do the integration on R. Okay, so first, before that, you need to know how to compute the pullback. You need to at least know the gamma star W before you can compute it on R. Okay, so any questions so far?
I did have it's kind of like a technical question.
Yeah.
When you have dt on both terms, shouldn't you have two integrals then?
Oh, I actually what I think. Oh yeah, sorry. Yeah. I was thinking. Yeah, it should be. Yeah, but I'm actually thinking about this is as a. I'm actually thinking about this is a before combination. It's a covector. Yeah. Yeah, I'm just thinking about combination. I should probably combine it into one, but yeah, I mean it's just a notation. But yeah, but you know what I'm doing. Yeah.
Thank you.
Okay, so now probably the couple last thing I want to do before the end of today is the following two important property. First property is essentially that the repenetration, right? So what we want to make sure is that when we do the repenetration of a curve, especially if the repenetration follow the same direction, I hope the definition of the line integral of my covector field should not depend on the how you parameterize the curve, right? Because otherwise it's not a well-defined definition, right? So first we need to define what a repenetration means. So repenetration just means, okay, if I have both smooth, piecewise smooth curve, right? It doesn't necessarily need to be complete smooth. And you have a curve gamma from a domain AB in real line to M. And then you have gamma delta, which is from another domain, another interval, compact interval. And we call this gamma delta to be the forward reparametrization of gamma if gamma delta is really just gamma composed with a diffeomorphism between the interval CD and AB. So it's really like, for example, repenetration of a curve just means that in some sense, how fast do you want to move on the curve, right? You can say that, oh, I move this curve along certain speed. Now I triple it, right? And as you can imagine, because you're going through the same track, right? So when you integrate a same covector field, it should not somehow depends on how fast you do it, right? So that's why like you should expect if the integral, the definition of integral is well defined, it should be somehow independent of this type of representation. So we say gamma delta is a forward representation if gamma delta is just gamma composed with diffeomorphism, plus this diffeomorphism is an increasing function, meaning you're going along the same direction, not backward, right? And of course, as you can imagine, I can also define what we call the backward. I'm just putting here the backward. If it's called backward repenetration, if phi is a diffeomorphism plus it's decreasing, right? So it means really literally like you're tracing the same curve backward, right? So now if that's the case, then you can see that we really have this independence of the parametrization. And this is what we call the parameter independence of the line integral we define. So if you integrate the covector field W over this repenetration gamma delta, it should be exactly the same as the integral of W over along this curve if gamma, over the curve gamma, if gamma delta is a forward penetration. And as you can imagine, if you go backward, then the integral should have a negative sign. So if gamma tilde is a backward representation, then your integral will differ by a sign. But this actually really shows us that the way we define line integral is nice and well defined. Okay, and seriously, this is really, you can just do the one line proof. So I'm going to do the one with forward penetration, right? So you can see that, okay, I want to integrate W over gamma tilde. This is really, by definition, you're doing like gamma tilde pull back W, right? This is the definition. And okay, here I need to do a little bit setups. Gamma tilde is CD to M, right? And because it's repenetration, and I want the forward one, so this is like this, right? Okay, and you can actually just write down, compare with the definition. This is CD, and gamma tilde is just really gamma composed phi. And here I need to use something that I didn't really kind of justify before, but this is easy to justify. I'm using this property that if you take the pullback of some composition of a map, this is a little bit different than push forward, right? Push forward, it comes from the differential. So if you have, say, F compose G and you do the push forward, you just directly can do dF compose dG. But for pullback, it's reversed. Actually, this is, in some sense, I'm using a property of pullback. So the pullback of gamma compose phi will actually be the pullback phi star compose gamma star. And you acting on, you pull back the W here. So this is the integral on CD. So I'm kind of using this. You can actually check it yourself. I want to be a little bit sloppy here. But as you can imagine that this would be the case. Okay, so now when you do this, then you can see that now we can, by what we saw before, right? This is phi is the diffeomorphism, right? So you have a diffeomorphism. So actually, I should probably do this, it's better, right? You first, now you pull back by phi star, right, of this whole thing. And this is the one we saw before, that the proposition 1131, right? If you integrate something by the pullback of diffeomorphism, it should not, this is the diffeomorphism invariance, right? So this is essentially the same as you do the integral on AB and of this thing that you pull back. Okay, and this is exactly equal, not with a negative sign. It's because the phi is, I'm assuming here that phi is forward. And as you can imagine that if phi is backward, then in this step, it will be negative sign. Then this is really nothing else but the definition of integral over, over gamma. So it's really just by the definition and invariance of the diffeomorphism. Okay, so the last thing I just want to talk about, like I don't want to go over time, so I just want to give you a heads up. On Thursday, I'm going to first show you like how to directly explicitly compute. Sometimes it will be easier to use the proposition 11.3a. Then I will move on to the very important thing is that it turns out that the line integral of covector field on the manifold will also have the fundamental theorem. So it will be essentially like this. If you integrate this particular covector field df, the differential of some real value, smooth real value function, then you will have the exact fundamental theorem of calculus that you saw before. And it's really, the proof is really using the fundamental theorem of calculus. So that's why this also shows that our definition of defining the line integral of a covector field on manifold through the pullback to R, it's well defined, because then we share all the nice things coming from the integral on R. And it actually has a nice property like such fundamental theorem. And this theorem essentially will tells us that, for example, if you're looking at this line integral, right, if you have this fundamental theorem, imagine if you have a closed curve, right, meaning the endpoint is the same as the initial point, then your through this line integral fundamental theorem, then the integral will be 0. So there's a lot of nice property here. Then this will brings us to the definition of conservative covector field, for example, and this is somehow related to the physics as well. Okay, so I will give you a little bit heads up. So coming back on Thursday, I will continue the rest of the things about line integral. And I think I will also be able to start the next thing I want to do on Thursday after this chapter is I'm going to just briefly mention what's the definition for tensor, because we are going to need to generalize the one form here to K form, K differential form. So right now for covector field or covector, essentially you input one vector. We can generalize this kind of linear map to something that you input, say, K vectors and output R. And this whole thing is linear with respect to each entry. This type of thing is what we call tensor, right? Or in particular, like a covariant tensor. So we're going to, once we can do this, then finally we can define the integration of n form. Because now you can see covector field, which is one form, we do one form integral of one form over something one-dimensional. But if you want to make sense the integration of something over something which is n-dimensional, then you need to pair with an n form. So one form with line integral, n form with something over n-dimensional manifold. Okay, so there's a rule we need to follow here. Okay, so that's basically the plan. So let me know if you have any question. Otherwise, you're free to go.
I have a question.
Yeah.
Just a quick question.
Yeah.
So for part 1D, so that's proving the part D of the proposition, that the fx and gy is equal to, and then like 3 terms.
Oh, sorry. What you're talking about the homework or?
Yeah.
Oh, I thought you mean the lecture notes. So I was like, I'm a bit confused.
Sorry.
No, don't worry. Let me check. So, give me a second. This is part 1 or part 2?
Part 1.
Okay.
It's just 1B. So it's proof part D of the proposition.
1. Okay, and what was your question? Sorry.
My question is, do you need like a dummy function?
Okay, so let me see. So vector field smooth function. So this is a vector. Yeah, I think it will be easier if you do the dummy function. Yeah, you evaluate acting on, when you evaluate at each point, you're acting on some function. I think it will be easier to see like exactly what this is, because otherwise, how would you know how it acts? So usually, because it's a vector field, so the best way to see how vector field acts is through acting on a function. Yeah.
Okay, so that means, so sorry, let me grab it real fast.
Let me also grab my book. Give me a second. Yeah.
Okay.
So let me see. This is proposition 8. Yeah, I think it's better you act like acting on the like what you call the dummy function, the test function. Yeah. So you give me like a actually you can see that how, if you have the book, you can see that this is how essentially how they prove it, part C, the Jacobi identity. Right? Because like usually when it comes to like vector field, right? Because you want to take the vector acting on some function. So in order to know what vector field looks like, the best way sometimes is really through how it acts on all possible function. Right? Essentially, you plug in what you call the test function or dummy function. Yeah.
Yeah. Okay. Okay. Because I think I just got confused because there was actually F and G in there.
Yeah.
So that's why I just wanted to make sure.
Yeah, like you called it something else, right? Maybe
Yeah.
call it like H or something. Yeah, that's why that you need to really be careful. Like don't confuse when you do the computation, because like yeah, your dominant function actually are also some function, smooth function in the same space, like C infinity of M. So yeah, so that code is something else. Otherwise, it will be very confusing. Yeah.
Yeah. Oh, I keep writing something, but then it keeps disappearing. I don't know.
Oh, you want to write on the on my board, or what do you mean?
Yeah, like I write something.
Oh, sorry, because I was not in the thing, so that's why. Let me open. Yeah, okay. Now it should be okay. I was not in the screen. Yeah.
Oh,
sorry.
you're good.
Yeah.
Okay. So just to clarify, this is what we want to show then. So I want to show fx, gy, and let's say like h. So we want to show this is fg, xy, h plus fxg, yh minus gyf xh. So that's what we want to show.
Okay, so be careful here, right? Let me see whether I can. So this should be you should treat this as a whole vector field acting on H, right? And here, what you will end up with is this new vector field acting on H. And then F times G is just a smooth real value function. And the second term, what you should think of is that because you have xg here, this is already x evaluate g. This is already a function. So what you have here is essentially your own y acting on H. And also here is x acting on H. Yeah, so that's how you want to be careful. Like this is not just y times f. This is already y evaluate f. This is already evaluate. Yeah. And you start, essentially what you do is you start with the left hand side, right? Then you use the Lie bracket definition, right? So you will have essentially fx gy acting. So this would be gy acting on H, right? But then you essentially take f times x acting on that, right?
Yeah.
And then you minus gy, right, acting on f times x acting on H. Yeah. So then you need to do like some product rule and all that, and then you're going to see. Yeah. So there should be some property that's, I think, let me see. Let me recall how much we're going to do. So I have, yeah, I think right away, just product rule, you will see the pattern. Yeah. And then the last thing, you just need to combine to the back to the bracket of x and y. Yeah.
Okay. Yeah, so I did solve this, but then it got brought up like maybe I have to use a test function.
Yeah.
So in order to be able to act on it, we need a test function.
Yeah, because you want to see, like essentially you want to see how this vector field looks like. But essentially the way we define vector field or vector in some sense is through by how it acts on the function. Yeah, that's why like it would be easier if you just say, okay, if you can prove that for any H, right, the test function, if the left hand side will always be the same as whatever the right hand side is, then you're essentially tell me that as if you evaluate at each point, it will be a tangent vector. Then tangent vector is essentially a derivation, some kind of map, right? As a map, like when you evaluate at every possible test function H, it looks like the same thing. So that's why as a map, it should be the same. As an action, right? A tangent vector, it should be the same. Yeah.
Okay. Well, thank you. This helped clear a bunch of stuff up. So
by the way, do you have like a couple minutes? Remember the question you asked me about your midterm?
About my midterm? Oh yeah.
Like the thing. Yeah. So what happened is that I remember you mentioned that you want to do the composition of the inclusion map and use the heuristic property, right?
Yeah.
So the things that with phi inverse, you can first with phi inverse, you won't be able to do that because then the domain doesn't match up, or the map you want to see doesn't match up. So with phi inverse, you can. But with phi, even though technically the domain match up, but what happened is if you really look at what the domain and is that, so phi is from X to R, right? X is the manifold we have in the problem 1. And I, like what we discussed, what you defined like back then is R to R squared, right? So this would be a map from X to R squared. But the question is, in order to know whether this map is continuous or not, it still goes back to the same question that you need to use the topology from X. So it really doesn't give you any advantage in some sense.
Okay.
Yeah, so it's from my point of view, and especially because the way you define things, right? You still, like, how do you say this map is continuous? Then you still need to say, oh, I have an open set here. And because this is X would still be not a general, it's not in R, or like it's like some spatial topology we have, right? Like a subset in R2, right? So the things that in order to say that this map from, if you're saying that, oh, I have a map from usual R to, I don't know, R2, for example, then it's easy to see because we have really the usual topology on real line and then the Euclidean space we know of. But this is not Euclidean space, right? So,
yeah.
So in order to say this map is continuous, then you back to the old question that, okay, you want to say any open set here, when you like pull back to here, like through the pre-image, is this open here, right? Then you will still need to go back to the same question by using the topology coming from X. So I don't see the advantage of doing this I compose phi thing, because then you can just directly show this thing, right? What's the difference between, do you know what I mean? Like you still need to go through the discussion of the topology on X. So it really doesn't give you any advantage. Yeah, so what you should do is really just directly see how you map, how the phi map, and then use the topology that defined in the problem 1 for X. And then essentially that's exactly the way I did it with my solution. Yeah. So that's essentially what I just want to tell you, that I don't see the advantage of, but the thing is that, if you can prove this is smooth, continuous, then indeed phi is continuous. But the question of proving both of them, either one of them to be continuous, the same, it's essentially the same question. If you think about it, right, phi compose inclusion, in some sense, it just kind of looks like phi, because it's an inclusion map. Yeah. So you don't get any advantage from there. You still need, so that's the problem, that I think the easiest way is actually directly do it through phi. Yeah, using the topology that we know. Yeah.
Okay. Yeah, so then I was pretty determined to
and then also the phi inverse, right? You cannot do like, first of all, because the domain for phi inverse, right? So phi inverse is from R back to X, right? So if you want to do the what's that called? If you want to do, is that right? Yeah. If you want to do the inclusion map, then you then you cannot compose with inclusion, right? Yeah, how do you compose with inclusion? Then the domain doesn't match up, right? Unless I don't think you can do the inclusion with phi inverse, because the domain doesn't match up, right? Yeah, I don't think you can do that. So that's why phi inverse will not work. Yeah. So so that's why, like, when you asked me last time, like, I was actually thinking about it, and I realized that like using this way may not necessarily gain you any advantage. It will, I mean, first of all, then you will not be able to justify whether phi inverse is continuous or not. Second, even you want to prove phi is continuous, it's the same question essentially. Yeah.
Okay, well, thank you for looking into it.
No, I mean, I actually, I want to tell you, like a while ago, but I keep forgetting each time. And then I was actually want to tell you on Monday, and then Monday you left earlier from the office hours. I was like, okay, then I'm just, whenever I can get a hold of Jackie, then I'll tell her. Yeah.
Sorry, these last few weeks have just been hectic.
No, I assume you are going to be super busy from now until like the end of April.
Going on
Yeah.
nonstop. Because even like even though I have 2 weeks to present my talk, I have a talk with